Here's a sentence that should not be true. Put a cup of boiling water and a cup of cold water into the same freezer, under the exact same conditions, and sometimes the boiling water freezes first, not melts less, not cools to match, freezes, solid, before the water that started out cold. If your brain just quietly rejected that sentence, good, that's the correct response. Because it violates something that feels like a law of physics. Hot water has more heat energy to lose before it hits 0 degrees Celsius. Cold water is already most of the way there. So cold water winning the race back to a freezer's temperature isn't just intuitive, it's basically what temperature is supposed to mean. And yet, this effect has been reported, tested, argued about, and occasionally reproduced for over 2,000 years. And as of right now, in labs today, actual physicists are still fighting about whether it's even real. This is the Mpemba effect. And I promise you, the story gets weirder the deeper you go. Let's start with where the name comes from, because it's a genuinely great story. In 1963, a Tanzanian high school student named Aristotle Mpemba was making ice cream with his classmates. The recipe called for boiling milk and sugar, letting it cool, then freezing it. Mpemba was in a hurry, so instead of waiting for his mixture to cool down first, he just shoved it into the freezer while it was still hot, squeezing it in next to a classmate's mixture that had already cooled to room temperature. An hour later, his came out frozen. His classmates hadn't even started. He assumed he'd made a mistake, so he tried it again, on purpose this time. Same result. Hot mixture, frozen. Cooler mixture, still liquid. When he asked his physics teacher about it, the teacher reportedly told him that what he was describing was impossible and that he must have measured something wrong. Which, credit to the teacher, is a very reasonable thing to say, because it does sound impossible. Imagine being a teenager, being told by an actual authority figure that your own eyes were lying to you, and just deciding, nope, I'm going to keep asking anyway. That's the whole reason this effect has a name at all. A few years later, Mpemba got the chance to ask a visiting physicist named Dennis Osborne the same question, this time at a public lecture, in front of an audience. Osborne didn't dismiss it. He had a lab technician actually run the experiment back at his lab, and the hotter water froze first again. They published it together in 1969, and the effect has carried Mpemba's name ever since. Here's the part that makes this even better though. Mpemba wasn't the first person to notice this. Aristotle wrote about it. Francis Bacon wrote about it. René Descartes wrote about it. For over 2,000 years, some of the most famous names in the history of science had independently stumbled onto the same weird observation, and every single time, it got treated as folklore instead of physics, right up until a teenager with an ice cream recipe refused to let it go. Okay, so what's actually happening here? Let's break down the leading explanations, because there isn't just one, there are several, and this is where it gets genuinely fun. The first explanation is evaporation. When you heat water up, some of it evaporates off the top as steam. Less water means less total mass that needs to be cooled down to freezing. It's a little bit like the difference between draining a bathtub and draining a shot glass. Less liquid, less time. Researchers have shown that a boiling sample can lose several percent of its mass to evaporation before it even reaches freezing temperature, and that alone can meaningfully speed things up. It sounds almost too simple to matter, but in a small enough container, losing even a little mass off the top changes the math more than you'd think. The second explanation involves dissolved gas. Cold tap water holds more dissolved air in it than hot water does, because heating water drives gases out of solution. The same way a warm soda goes flatter faster than a cold one, all those bubbles racing for the exit the second the temperature climbs. That dissolved gas in the cold sample can actually get in the way of ice formation and can also change how heat moves through the liquid. Less gas, in some setups, means a cleaner, faster path to freezing, which is a genuinely strange thing to say out loud, that water with less stuff dissolved in it can sometimes freeze faster, but there it is. The third explanation is convection. Hot water sitting in a container develops much stronger internal circulation than cold water does. Warm water rising, cooler water sinking, constantly stirring itself. That stirring can mean the hot sample loses heat unevenly, but efficiently, actually forming a layer of colder water at the surface faster than a static, cold sample would. Sort of like how a crowded room cools down faster once someone finally opens a window and gets the air actually moving, instead of just sitting there being generally cold and stale. And the fourth explanation, probably the strangest one, is about how ice actually starts, called nucleation. Water doesn't necessarily freeze the instant it hits 0 degrees. It can supercool below freezing and just sit there as a liquid, waiting for something. A rough surface, a dissolved particle, a tiny air bubble, to give the ice crystal a place to start forming. And this might be the strangest twist in the whole story. A study published in 2025 by researchers including James Brownridge and a team working with ice nucleating agents found that when both a hot and a cold sample are placed into a freezer that's saturated with these nucleation triggers, the hot water didn't just start freezing faster, it froze to a greater depth, and the effect got stronger the bigger the temperature gap was. Here's your real-world way to picture this. Think about starting a campfire. It's not really about how much dry wood you're holding, it's about whether you've got a spark and the right conditions for that spark to catch and spread. Water freezing works the same way. It's not purely about how much heat has to leave the water. It's about whether and where an ice crystal actually gets a foothold to start growing. Hot water, cold water, dissolved gas, convection currents, all of that changes where and how easily that first spark of ice catches. Now, here's the misconception, and I want to be really direct about this one, because it's everywhere online. People often explain the Mpemba effect by saying something like, the hot water loses energy so fast that it basically skips past the cold water's temperature. That's not correct. And it can't be correct, because of one of the most locked down principles in all of physics, conservation of energy. If the hot water starts at, say, 90 degrees Celsius, it must pass through 80, then 70, then 60, all the way down through the exact temperature the cold sample started at, before it can go any lower. There's no shortcut, no skipping, no magic loophole in thermodynamics. What can happen is that the hot sample passes through that shared temperature and keeps going faster than the cold sample cools from that same point, for reasons like evaporation, convection, or nucleation differences. It's not defying physics, it's exploiting physics in a way that isn't obvious until you actually watch it happen. And now, here's the part where I have to be honest with you. Because a responsible science channel doesn't get to just pick the version of the story it likes best. Whether the Mpemba effect is even reliably real is still, right now, a genuinely open and contested question among physicists. In 2016, researchers Henry Burridge at Imperial College London and Paul Linden at the University of Cambridge ran careful experiments and reported that they could not observe the effect at all, no matter how they set things up. Their paper's conclusion was blunt. Hot water simply does not cool more quickly than cold water under controlled, well-defined conditions. Meanwhile, other physicists, including researchers who've studied the effect in materials beyond just water, like crystalline polymers and certain minerals cooling in magnetic fields, argue that the effect is not only real, it might be a much broader phenomenon in physics than anyone originally suspected, something that shows up whenever a system is pushed far out of thermodynamic equilibrium. So which side is right? Honestly, we don't fully know yet. Part of the disagreement comes down to something almost embarrassingly simple. Scientists don't even agree on exactly how to define frozen for the purposes of the experiment. Do you measure the moment the water hits 0 degrees? The moment the first ice crystal appears? The moment the entire sample is solid all the way through? Different labs have used different definitions, gotten different results, and then argued about whose definition was the real one. One physicist involved in the debate has publicly said an entire competing explanation just makes absolutely no sense, which is about as close as scientific journals get to a public argument in a group chat. It's a genuine, ongoing scientific controversy, not a settled fact with a tidy answer. And that's honestly one of the more interesting things about it. This isn't ancient history. Physicists were publishing dueling papers on this as recently as 2025. And the disagreement isn't just about water anymore either. Some researchers have gone looking for Mpemba-style effects in completely different materials. Crystalline polymers, ice-like solids called clathrate hydrates, even certain magnetic minerals cooling in a magnetic field, and found hints of the same weird pattern showing up again and again. Which raises a bigger question than, does hot water freeze faster? It raises the question of whether this is secretly a much broader rule about how any system behaves when it's pushed far out of balance, not just a quirky footnote about your kitchen freezer. Here's a fact that tends to catch people off guard. If your hot sample starts at 99.9 degrees Celsius and your cold sample starts at 0.01 degrees, obviously the barely above freezing water wins every time. That's not the Mpemba effect. That's just common sense. The actual scientific claim only kicks in under specific, fairly narrow conditions, particular container shapes, particular starting temperature gaps, particular freezer environments. It's not a universal law that hot water beats cold water. It's a fragile, situational effect that seems to appear only when several of those factors, evaporation, gas content, convection, nucleation, line up in just the right way. Which might explain why some labs can trigger it, and other labs, using what looks like the same experiment, absolutely cannot. So next time somebody confidently tells you hot water definitely freezes faster than cold water, or, just as confidently, that it definitely doesn't, you now know the actual answer is more interesting than either. It might depend on your freezer. It might depend on your container. It might depend on invisible nucleation sites you'll never see. And after 2,000 years of Aristotle, Bacon, Descartes, a Tanzanian teenager and his ice cream, and physicists in 2025 still publishing contradictory results, we still don't have a single, clean, universal answer. Which honestly is kind of the best part, because it means the next person to actually crack this wide open, to figure out exactly when and why it happens, could be reading a chemistry textbook right now, or making ice cream.